Okay, what are the equations that I can form? Let us try to first understand that. We have done a very similar question in last class where we could conserve the mechanical energy as well as the momentum, linear momentum. Do you remember that?
Yes, sir.
This question is very similar to that. Initially, the system was like this. Suppose the rod was like this and this car was like this. Car has a total mass 2m with the rod, vertical rod, right? So it is the initial position of the system. When I release it and this red color rod becomes vertical, at this particular instant, the situation somehow looks like this. If you can visualize, the situation looks like this, and just before this rod becomes vertical, I can show the system like this. Yes or no?
Yes, sir.
At this instant, let us assume that the velocity of this trolley in this direction is v, and velocity of the center of mass of the rod will be in horizontal direction u, as well as the angular velocity of the rod is omega. Can I assume all these terms?
Sir, V will be to the left side.
Yes. Even if you have assumed it to be right side, you will find it negative, because I can easily say that the linear momentum of the system initially was
Yes,
0.
sir.
So if this red color rod is moving right side, this card will definitely move left side.
Okay, sir.
So what equations I can form? Let us form the first equation as conservation of
Momentum.
energy. Okay. Let us write down first conservation of mechanical energy. So what is the initial energy? As there is no work done by external force on the system, right? So we can assume that the total mechanical energy remains a constant. What is the initial total mechanical energy?
MgL.
Is it mgl? What is the initial mechanical energy? Yes?
Mg2L.
2L. Why 2L?
It is MgL only.
Why you are saying mgl? Where was the center of mass of this rod?
Oh yes, sir.
Where was the center of mass of this rod?
Mg L/2.
Yes, if you assume this to be my zero potential frame, this is my zero potential frame, then it must be mgl by 2. If you take this...
Oh, sir, I have considered that bottom one zero potential.
Alright. Then you are correct, but I will assume this to be my zero potential line. So mgl by 2 will be my initial potential energy of this red color rod. I do not have to write the potential energy of this car because it remains constant throughout. Can I say that potential energy is transformed into the kinetic energy of the system, because finally I have assumed 0 here. So no potential energy will be there on the system, entirely kinetic one. Can you tell me what is the kinetic energy of this system?
Yes, sir. Half mu square plus half into 2m into v square plus half into ml square by 3 into omega square.
Come again.
Yes, plus half into ml square by 3 into omega square.
Is it correct, everyone? Do you agree it? Do you agree with that? or it needs any modification?
I think this is correct.
What equation you have written? Half 2m v square is the kinetic energy of this car. It is right. What is the kinetic energy of the red color rod?
Half mu square.
Half mu square is the kinetic energy of its center of mass. Yes or no?
Yes, sir.
And what is this one?
Sir, please wait. So it will be
What the thing
m
is
square by 12 it will be. M square by 12. Half into m
Yes.
square by 12 into omega square.
Yes.
Sir,
It
but
will.
length is 12.
What length is 12? The lengths are given L and L.
Eh?
The length is 2 meter.
Oh my goodness. Okay, sir. I was misinterpreting it. As
So
12.
half m u square plus half ic omega square. Remember, right? I have seen many students do a mistake here. They write half ml square by 3 omega square. You cannot take ml square by 3 about this point because this is not a fixed axis of rotation here. Right? The axis of rotation itself is moving. So if it is moving, you cannot write about this axis of rotation. You have to take always ic omega square, half ic omega square plus half m bc square.
So about what can't we take?
About this axis, the top ml square by 3 omega square. Why we can't take that? Because it is not fixed. Yes, it is not a fixed axis.
So this equation is wrong.
Which equation? This equation is correct. If you keep it as 3, then it is wrong.
Okay, sir. That I understood. Of center of mass. Okay, sir.
Yes. So it is the total energy equation that I can write. The first equation is energy equation. That is only important for rotational motion. The rest of the part is okay. We have already done in our previous chapter. Now is conservation of linear momentum. We have done it on last chapter. What equation I'll write?
Sir, m into u is equal to 2m into v, or mu minus 2m.
Yes, mu minus 2mv equal to 0.
Yes.
That is the second equation. But 3 unknowns are there, u, v and omega. I need one more equation.
So omega you can get, that is L by 2 into v. Sorry, u.
Yes.
What I'm saying, so L omega by 2 is equal to u.
Is it L omega by 2 equal to u? Whenever you write constant equation, be careful. That is where students again do mistake. Constant equation. Now I will write my constant equation. Don't be in a hurry in writing constant equation. Draw your diagram correctly. Suppose the velocity of this point is u. I have assumed it to be u. And the angular velocity is omega. Right? Angular velocity is omega. That I have assumed. So if I now write what is the velocity of this point with respect to center, first I will write. What I will write with respect to center?
It will be L by 2 into omega.
Right or left?
So omega. It was right only.
L by 2 omega.
Sir, left.
Left. L by 2 omega is towards left.
So which one are you calculating with respect to what?
This point with respect to this point. The topmost point with respect to the center.
Okay, sir.
It is L by 2 omega right side. So with respect to ground, what can I write it? With respect to ground, what will be the velocity? Minus u. So can I say L by 2 omega minus u, as it is now connected, this
Yes,
point is
V.
connected with the car, yes or no?
Yes, sir, it's V.
It's V. So that should be your constant equation.
So please wait a bit.
Check everything if it is clear. Constant equation, linear momentum and energy conservation.
Okay, sir. Clear.
Now it is easy to solve this question again. If I know u is equal to 2v, and from here I can say 3v is equal to L omega is equal to 6v. Right? L omega equal to 2 into u plus v. Now u plus v is 3v. I will put replace u and L omega by v and I will find the value of v. If I first cancel m by 2 from both the sides, so it is gl is equal to u square means 4v square plus 2v square plus 1 by 12 L square omega square means 36v square. So 3 plus 2 5 plus 4 9. 9v square is equal to gl. So the value of v you will get 1/3 root over of gl. Value of u is 2/3 root over of gl. And value of L omega is equal to 2 root over of gl. 6 by 3. The question asks what is the speed at the end of the rod. So if this is point Q, this is point P, what is the velocity of point P? Can you tell me what is the velocity of point P?
So at first we'll it will be u plus L omega by 2.
Yes, good. About center of mass, it is L omega by 2. About center of mass, it is L omega by 2. And with respect to ground, it is u plus L omega by 2. So it will be 5 by 3 root under GL. That should be the answer of this question. We will find an important relation between angular momentum and torque. Okay, very important relation, but very easy to prove and as well as to understand. Angular momentum, we know it is m cross p, m into r cross v. So if I now differentiate this angular momentum with time, what I will get? Should I write it as m dr dt cross v plus m r cross dv dt?
So please wait, sir.
Yes, sir.
So the order of cross product will remain the same, so?
Yes, definitely.
Okay, sir.
So what is dr by dt? What is rate of change of the position vector?
B.
Velocity. And what is dv by dt?
So it's A.
Acceleration.
Now v cross v is how much?
0.
0. And what is r cross ma?
R cross MA.
Is it r cross f?
Torque. Torque.
So the simple relation is dl by dt is equal to torque.
Yes.
You should relate this equation with Newton's second law, where we found that dp by dt is equal to f.
Yes, sir.
Right. Similarly, dl by dt is equal to torque. And if I ask you what is the direction of this torque?
So same.
Same as what?
Same as angular momentum. Change in angular momentum, sorry.
Yes. The direction of torque is not along the angular momentum, but the direction of torque is along the change in angular momentum. Right?
Yes.
Direction of torque is along the change in angular momentum. Not along the angular momentum, along the change in angular momentum. Alright, dl by dt equal to torque. So I can also say that if tau is 0 about any point or axis, what can I say about the angular momentum?
It is constant.
Constant.
Angular momentum is constant about same point or axis?
Yes, sir. Yes, sir.
This is known as conservation of angular momentum. You can also relate with this principle the conservation of linear momentum principle. What was that? If on a system of particles the net force is 0, the linear momentum of the system always remains constant.
Yes, sir.
It also says the same thing. If on a system of particles or on a rigid body, whatever you can take, if the net torque about any point or axis is 0, you can always say that the angular momentum is constant. Right? And that is also a very important conservation law of mechanics. Basically, we can also only have three conservation laws: energy, linear momentum, and angular momentum. Sometimes you will find that you cannot conserve linear momentum, but when you can conserve angular momentum, you can simplify the question much. Right? For example, suppose two balls are there. One is of positive charge, another is of positive charge. Right? This positive charge is at rest. So these two charges will repel each other, yes or no?
Yes, sir.
Now if you send this positive charge towards this positive charge along this line with a velocity u, then can you conserve the linear momentum of this charge?
Can you repeat the question?
I am saying that two charge balls are there which are repelling each other. I have thrown one charge particle with a velocity u. Can I conserve this linear momentum of this charge particle?
No, sir, I can't trace the velocity of the balls then.
The velocity is going to be like changing.
Yes, so why I cannot, I'm not talking about velocity, forget about that. Why I cannot conserve its linear momentum? What is the correct explanation for that?
So please wait.
So there is a force acting.
Because there is a repulsive force, yes. Because of the repulsive force acting on the ball.
The force acting and there is a velocity, so basically the cross product gives a torque.
Whose cross product is torque, force and velocity?
No, I was not saying that. I mean, it's not exactly like that. I mean, the thing is, it gives a torque to this.
It does not produce any torque. It is only a force, and if the particle is experiencing a force, I cannot conserve linear momentum. That's all.
So if I take the two particles as a system, then
can I also conserve their linear momentum? If I take them as my system, then this force.
I didn't get your last sentence.
I'm saying if I take this two as my system, then also can I conserve linear momentum?
No, sir, not before that. What you said, if there is force.
If there is force, I cannot conserve linear momentum. That was my statement. Think about the particle 1 and 2. My first question was, can I conserve linear momentum of this particle 1?
No, sir, due to net external force.
Because there is net external force. Second question, can I conserve linear momentum of 1 and 2? Yes or no?
So we should be able.
No, because this point 2
I
is...
think no, because the fixed external force is there
Yes,
into.
this is fixed. So some external force is still there.
Okay, sir. Okay, sir.
If external is there. So linear momentum.
Sir, I have a doubt on this part.
Yes?
Sir, if the force applied is in like direction of the velocity, then how can we not conserve angular momentum?
Have I ever told about angular momentum so far? What I am telling the linear momentum or angular momentum. What you are discussing?
Oh, sir, are you talking about linear momentum?
Yes, I'm talking about linear momentum.
I thought you were talking about angular momentum.
We are talking about linear momentum.
Okay, sir, I guess.
Linear momentum of the system, linear momentum of the particle 1 is not constant, it is not conserved. Linear momentum of particle 1 plus particle 2 is also not conserved.
Not conserved.
Now my question is, can I conserve the angular momentum of the particle 1 about the point O?
About 2, though? Yes,
Yes.
sir. Yes, sir.
Why I can conserve it?
So because the net torque will be
Because
0.
the force itself always passes through the point O. So torque will always be 0. So angular
Yes.
momentum of 1 with respect to O, that is a constant.
So means about the direction of force, we can always conserve linear momentum.
Linear momentum.
Oh, angular momentum. Sir, I'm confusing with my words.
Angular momentum you can conserve, yes. If it passes through the point about which you are taking angular momentum, definitely you can conserve.
Yes, sir.
You only have to check about the torques. If it is 0, you can definitely conserve your angular momentum. Right? So you will encounter different types of questions like this where you cannot be able to apply the linear momentum conservation principle, but we can conserve energy. Here we can conserve energy or not? Conservation of energy?
Yes, sir. There is no problem
Yes,
with energy.
is applicable. Conservation of energy is applicable because there is...
Yes, sir, but I have one question.
Yes.
So if the force that is fixing that point, particle 2 is
Yeah.
non-conservative?
Even if it is conservative, non-conservative, does it do any work? Does that force do any work? Because this is fixed.
No, sir. Okay.
No. Then energy is always conserved. You need two equations. You will find one equation by linear momentum, angular momentum conservation, another by energy conservation.
Yes, sir.
Understood? I am not going to solve this question right now. We will definitely solve them in class 12 when we will study electrostatics. But this type of questions you will encounter where we can conserve linear momentum or angular momentum or energy, right? We have these three different conservation principles now with us. Okay, what I was telling you that now we will try to prove this tau is equal to dl by dt by taking a few examples. One simple example is that if I say that suppose I have a particle of mass m and I have projected it in xy plane like a projectile motion. Gravitational force is acting downward and I have projected the particle in this xy plane.
So means it is the normal projectile, so in gravity.
Yes. Initial velocity is u at angle theta. I have projected it. The mass of the particle is given m. Gravity is acting downward. So you need to calculate the angular momentum as a function of t about the point O. Can you tell me what is the angular momentum?
So I couldn't hear you for last 1 minute, sir.
I only asked you to calculate the angular momentum of that particle about point O as a function of time.
Okay, sir. Trying, sir. So may I try, sir?
Yes, tell me what's your answer?
Sir, means I am giving the direction also, sir. It will be mg t square into u cos theta by 2 minus k cap.
Yes. Look, after some time, if I say it is the velocity vector, and the velocity vector has two components. One component along this line, horizontal component. What is the horizontal component of the velocity vector? Can you tell me what is the horizontal component of the velocity? U cos theta only. And what will be the vertical component of the...
Sir, can you repeat from the beginning?
It's from the beginning I'm saying that suppose after time t the particle is here where the velocity is v. So what is the horizontal and vertical component of the velocity vector?
U cos theta উপর দিকে হচ্ছে u sin theta t u sin theta minus gt.
Minus gt.
U sin theta minus gt. About point O, if I have to find the angular momentum, then I have to also find that for this horizontal velocity, I will take this vertical height from point O to this vertical distance. Yes or no?
Yes, sir. Yes, sir.
And what is this vertical distance?
Sir, it is u sin theta t minus gt square by 2.
Minus half gt square. And for this u sin theta minus gt, I need that horizontal distance. Yes or no?
T.
U cos theta.
U cos theta into t. So now I can find what is angular momentum about point O. If I do a cross product of r cross v, where v is u cos theta, in which direction my product will be?
So what v is u cos theta though? So please wait. It will be into the plane.
Means
Angular
minus k
momentum.
cap. So can I say it
Yes.
is u cos theta multiplied by u sin theta minus half gt square along minus k cap?
M.
Yes, sir.
M is there. And what about this vertical component? If I do a cross product of r cross
It will
v,
be in positive direction.
so it
Then
is
upor plus k cap.
plus m ut cos theta multiplied by u sin theta minus gt k cap. Now if I simplify it, mu square t cos theta sin theta, mu square t cos theta sin theta. Can you see this term will get cancelled out, minus k cap and plus k cap?
Yes, sir.
So mu minus half gt square and mu plus half gt square cos theta. So is it minus mu half gt square cos theta?
Yes, a simple addition. Yes.
So it is a very simple way to calculate angular momentum, but if you just do it, that let us take dl by dt. Here, what is variable?
So L is variable, theta is variable.
Is
No.
theta variable?
No, sir. T is
Only t is
T
variable.
is the variable. T.
So if you do it minus mug by 2 cos theta into 2t.
Yes, sir.
So what you will get, minus of mg into u cos theta t.
Yes, sir.
Now at any instant, at this instant, what is the force on this particle?
Sir, please wait, sir. Sir,
Yes.
sir, means what can you please explain from the dLdt part?
2t square, the differentiation is 2t. So 2 gets cancelled out.
Direction will be retained, so.
Yes, the direction is the same. Angular momentum about point O at any instant is the same, minus k cap only.
Okay, sir. Okay, sir.
Right. So what is the, I am getting what is the magnitude part? The magnitude part is mg into ut cos theta. Can you see that if I ask you what is the torque of mg about this point O?
Yes, sir. Mg into ut cos theta. So we can tell it by seeing only.
Yes. And what is the direction of the torque? Is it the same
Into
as
the plane.
minus k cap?
Yes. Yes, sir.
Yes, sir.
So look, tau is equal to dl by dt. That also you can do it.
Yes, sir.
And you can also reversely apply this concept to calculate the angular momentum. You can find the angular momentum by simply integral of tau dt.
Yes, sir.
Right. So L will be, initially L was 0 and finally L, suppose L vector. So it is tau means mg into ut cos theta minus k cap. If you integrate it, you will eventually find the same answer, minus mu by 2 gt square cos theta.
So please wait, sir.
Right. So alternately, you can also use this equation dl equal to integral of tau dt to calculate the torque.
So please wait a bit.
Yes.
See, initially you have taken 0, so that angular momentum.
Yes. I have not taken 0. It is 0 because initially velocity is passing through point O.
Yes, sir. And then you have.
Done? Okay. Alright. Now, a very interesting phenomenon we can explain by this principle of the equation of torque and dl by dt. Suppose, let us assume that you have a bicycle wheel, right? And you have a bicycle wheel. What you have done, you have taken one bicycle wheel. It is the axis of that bicycle wheel. And you have connected this end of the axis with a thread and joint connected at the ceiling. Okay. It is a bicycle wheel. You should visualize it.
Sir, wait a axle ta to rod.
Yes, this white color is the axle of the bicycle wheel. Right. This part is coming towards us and this part is going away from us. Okay. Now my simple observation is case 1, if I release it without rotating the wheel, if I release,
so which one is front direction, can you please say?
This is the front. This is front,
Okay,
right? This is the front wheel, front part of the wheel. If I release it without rotating, without any rotation, about axis. Axis means this white axis. What will happen? We all know what will happen if I just release it.
Fall down. Fall down.
It will fall down like this. Yes or no? Can you tell me why it is falling down?
Angular momentum about the fixed point.
If this point is fixed. This point is fixed.
MG is providing a torque to it.
Yes. Can you say that mg force is there and mg is providing a torque about 0.0?
Yes, sir.
And what is the direction of this torque?
Into the plane.
Into the plane. Let me draw the axis. It's x-axis, y-axis and z-axis. What is the direction of the torque?
It will be y-axis.
Torque is along y-axis. And you can find that angular momentum. What is the direction of angular momentum of that body?
So initial.
Initially 0.
Mm-hmm.
Finally it is rotating in this direction, omega. Yes or no?
Sir, I am saying that, can you please re-explain where the body will go after leaving it?
That you can understand. If I release it, this white axis, how this white axis will move?
It will move frontwards, like.
Frontwards. Or it will move
Backward.
downward like this. Yes or no?
Yes, sir.
So if it is moving downward, what is the direction of angular momentum? Every point is moving with velocity or omega. So angular momentum is definitely along y-axis.
Yes, sir.
Right? So you can say that the change in angular momentum is also along y-axis.
Sir.
Yes.
So this part this angular momentum part I didn't get at all.
What is angular momentum? If you take any point, let us assume this point. Now what I will do, now I will take the same bicycle wheel. I'll take the same bicycle wheel. But only what I will change, suppose this is the axis of that bicycle wheel. I have connected the end here only. Right? And suppose these are the spokes of that. Now I will, before releasing this bicycle wheel from here, I have just given this bicycle wheel an angular velocity like this. So this part which is coming, yes, this part is coming, you can also imagine this is like this, angular velocity like this.
Okay, like that.
Now all the particles are moving in circular path. So now if I ask you what is the angular momentum? What is the angular momentum about this point?
Which point?
About this point or axis. The same angular momentum you will find about the point or axis, because all the particles are moving in this circular path. So can you find the angular momentum is along this line?
Yes, sir. Yes, sir. Yes, sir. Yes, sir.
Everyone, can you visualize the angular momentum?
Yes, sir.
All the particles are
Yes,
now
sir.
moving in circular path. So if you just do m r cross v, you will find all of them are along the same angular momentum L. Now look what happens. Now if I ask the angular momentum, what is the property of angular momentum? Angular momentum will always change in the direction of torque. Here there was no angular momentum. So in order to chase the torque, angular momentum increased in this direction. But here I have an initial angular momentum.
Yes.
Now if I ask you what is the direction for the change of angular momentum, what should be your answer?
So means direction of torque, it should be into the plane.
And what is the direction of change of angular momentum?
That only, that is into the plane, no?
Is it
Into
the same direction of angular momentum change? Yes
Sir,
or no?
change will be into the plane. And what you asked, another one?
Yes, I am only asking the change in angular
Yes,
momentum.
change is into the plane.
The same as that of torque.
Yes, that.
Now,
Yes.
if you see...
Sir, can you please repeat this part once?
Okay. Do you remember the expression dl by dt equal to tau?
Yes, sir.
From there, what we can say about the direction of the change in angular momentum?
No, sir, not this part. Sir, before that you told that it will change. So that part I didn't.
That is only I am explaining. That what is the direction of for the change in angular momentum? Angular momentum कौन direction में change होता चाहिए?
Torque की direction सकते.
So I can only say that angular momentum will change in the direction of torque. Here also, the torque is along y-axis, so the change in angular momentum will be along this axis. Now try to understand. Try to clearly visualize the situation from top. If you can.
Top view.
Yes, top view. Top view of this situation. Only think about this axis. Angular momentum was along the axis.
Yes, sir.
Initial angular momentum was along the axis. After a very short time interval, a very small time interval, where will be my angular momentum such that the change is along y-axis?
Sir,
It
that
is
will
the-
be a very less upward to that.
Yes. Can I say after a small time interval, the angular momentum will be somewhere here
Yes, sir, that thing.
along this line, such that the change in angular
I
momentum.
couldn't get this.
Yes. What is the change in angular momentum now?
Sir, I could not get this part, sir.
No problem. Try to visualize it. I can explain it. If you see from top, can you see this is my x-axis
Yes, sir.
and it is my y-axis?
Okay.
Are you convinced with that?
Yes, sir.
And it is the initial position of the bicycle wheel.
Okay.
It is the axis of rotation of the bicycle wheel.
Yes, sir.
And this is the L vector initially.
Yes, sir.
If the change in L vector is in this direction, then what is the final L vector? Isn't it in this direction?
Yes,
Sir,
sir.
he was saying upward.
What I am
That
saying,
thing I'm saying.
if
A
this
bit
is
upward.
L vector, this is dl vector, then what is after final L vector? Is it this one or not?
Yes,
Sir,
sir. It
at
will
the
be.
plane which you have in the third figure, is it the plane of XY plane or it's the
It's
XZ plane?
XY plane. It's XY plane. I'm looking from top view. Z is towards you.
Sir, he was saying upward, that only I'm confused.
Upward means in XY plane upward.
Okay, he was telling that one. Okay, sir. Okay, sir.
Can you see that final L prime
Yes,
vector?
sir.
Final L prime vector is along this line.
Yes, sir. I got it, sir.
So where will be your final, after some time, where will be your bicycle wheel? Will be
Yes.
here or not?
Yes.
Yes, sir.
So will it perform a circular motion?
Yes. So now if you see that as time goes, your bicycle wheel now will not come down. Instead, your bicycle wheel starts rotating
About the
in
thread.
XY plane in a circular motion.
Yes, sir.
Yes, sir.
Right. You can always try this at your home with any object, right? If you can construct similar type of configuration, you just rotate it. This is known as rotational equilibrium. So if something is at rest, it will fall down. Suppose a bicycle, when you are not riding a bicycle, when you are this is at rest, can you just release that bicycle on the road and it will be staying there? No.
No, it will just incline.
Yes, it will fall down. But as soon as you give it an omega, you will provide it an additional stability.
Yes, sir.
Right? And why that is? Because that angular momentum always chases the torque vector. That the change in angular momentum rather will always chase the torque vector. Means angular momentum will change in the direction where you have a torque vector.
Sir, I have a question.
Yes. One second. In
Sir,
the second case, if we provide an additional omega to the wheel, L vector or the wheel will rotate in XY plane.
Sir,
instead of coming down. হ্যাঁ
Sir.
বলো।
হ্যাঁ, so আমি বলছি যে ওই যে L প্রাইমের ডিরেকশনটা মানে along that white line, so that bicycle will be along that blue line তো?
Yes, this is the bicycle wheel. This is the bicycle wheel.
Okay,
Blue
sir.
line is the bicycle wheel. Right?
Sir, will the magnitude of omega change?
No, magnitude of omega has nothing to do with that. Only the direction, the torque is the rate of change of the angular momentum. Here the direction, here the magnitude remains same, but the direction is changing. Right? No one is there to change omega. Okay?
Yes, sir, got it.
Alright. Now, as we know what is the principle of momentum, angular momentum conservation, and what is angular momentum. Now, till now we were only considering angular momentum of point masses mostly. Right? Now we will discuss what is angular momentum of rigid bodies. Very important to understand. What is angular momentum of rigid bodies? There are two possible cases. Case 1. Case 1, when the rigid body is in pure rotational motion. What do I mean by pure rotational motion?
Sir, means all parts are in same omega.
All parts in same omega is always there in a rigid body.
Sir.
What do I mean by pure rotation? Can anyone say that? What is pure rotational motion?
So no translation.
Pure rotation means, yes, no translation. Pure rotation means every part is moving in a circular path.
Yes, sir.
Right? Pure rotation means each and every particle is moving in circle about any point or axis. So if the body is in pure rotation about any point or axis.
So why not same omega, sir? Means why did you reject that?
I'm saying that same omega is always there. Even if the body is in translational motion, is the omega changes from one body to another?
No, sir.
No. So I'm saying that pure rotation and combined motion, both are having the same omega. So omega you cannot, with omega you cannot identify them. Pure rotation means every point of the body is rotating in a complete circular motion. So if I say that this is a rigid body, it is a rigid body, and this rigid body is in pure rotational motion about this axis, right? Then suppose the angular velocity is omega. Let us assume this is a point mass mi, the position vector being ri. What is the velocity vector of this point mass? Ri omega.
So please repeat from that mi part, sir.
A simple point mass you have taken, the position vector from the axis is ri, and the velocity should be ri into omega, perpendicular to this.
Yes, sir.
So now if I ask you what is angular momentum of this small mass about this point, mri cross v.
Yes, sir. Yes, sir.
And what is the direction of mri cross v? If I make it a summation, I will find the total angular momentum.
Sir, it is in y, positive y.
Or along the omega vector itself?
Yes, sir.
Right?
Omega.
So can I say it is m r square into omega?
Sir, please wait a bit.
Omega is same for all the particles, yes or no?
Yes, sir.
So I can take it outside. And as the distance, as ri vector and v vector are perpendicular, so the magnitude is always r square into omega. And direction I can do it by omega vector.
Sir.
Huh.
So this part I got a bit confused.
Which part? Tell me what's your question. Ri cross v, is it okay?
Yes, still that it's okay after that.
What is Ri cross v? Let us write down one more step. Ri into v is Ri cross v. What is the magnitude of Ri cross v?
Sir, it is Ri square into omega.
Sure. And what is the direction of it?
Omega cap.
Right? Can I take this mi Ri square inside the bracket and omega cap outside it because it is a constant?
Yes, sir. Okay, sir. Got it.
What is this bracket inside the bracket? What is the term?
So that's I.
So angular momentum about any axis, can I say it is I about that axis into omega? Yes or no?
Yes, sir. Yes, sir.
Yes, sir.
When I can use this formula? When I can use this formula? When the body is in pure rotation. If it is not in pure rotation, can I say its velocity is r omega?
No, sir.
No.
There's something else also.
So that is why I have mentioned it. When the body is in pure rotation about any point or axis, I can say the angular momentum about that point or axis is, basically axis we will talk, and axis is Ia into omega. What is moment of inertia? Ia is moment of inertia of the body about that axis.
Sir, please wait a bit. Okay, sir. Got it.
Now, if I ask you that a body is moving in rotation as well as translation, combined motion. Okay. And if I ask you to find angular momentum about any point inside the body, can I use the same formula?
About any point inside the body, so?
Yes.
Sir, I think you can use the same formula.
And why it is? Even if the body is not in pure rotation from ground frame, but if I think about a point inside the body, Can I say about that point or
And
axis?
for me, the whole body is at rest.
Yes.
For that body.
For that point, the entire body is in pure rotational motion.
Yes, sir.
Right. What I'm trying to say again for everyone, that suppose this is a rigid body which is rotating with omega and also it is moving with some velocity v. But if I ask you what is angular momentum about this point P, now if you just imagine yourself at point P with respect to P, what is the motion of this rigid body?
It's just rotating.
Is it a pure rotation or not?
Yes, sir.
Everyone, do you agree with that?
Yes, sir.
Yes. If I am sitting inside a point of the body, then I can always use this formula. So this formula is also applicable, also used with respect to any point in the body. Any
Sir,
point.
can you please repeat this part?
Sir, can you
Yes.
please repeat this part from beginning? My net was unstable.
Inside the body. Yes. Do you understand this equation? LA equal to IA omega. Have you got this
Yes.
part? Now, while applying this equation, I have told you that the body should be in pure rotation about any point or axis. My
Yes.
next question was that even if a body is in pure rotation, not in pure rotation from ground frame, it has a translational motion as well as a rotational motion. But if I ask you to find angular momentum about any point or axis that is fixed inside the body. Suppose P point is a point inside the body. I asked you to calculate the angular momentum about point P. Can I use the same formula? The answer is yes. Why?
Yes, sir.
Because
True, sir, true.
about point P, what is the motion of the body? About point P,
Rotation.
is it pure rotation? Yes. If it is pure rotation, I can always use it.
Okay, sir. Got it.
No problem. But
So then it will be IP into omega. So
yes, it will be IP into omega. Now case 2 is more general case. If the body is outside the, if the point is outside the body. If the point is outside the body.
outside the non-pure rotating body.
Any body, any rigid body, even if it is in pure rotation, about any outside point, it is not, every point is not in a pure circular motion. Can I say that?
Okay.
So if the point is outside the body, I can use this formula. Any point you can take outside the body. What formula I will use? I will first write down the formula. If you want, I can
Sir,
prove it. Yes.
So if I am outside at rest and
Yes.
in case 1, if the body is purely rotating, then why not it is all are in circular motion?
Look, all are in a circular motion, but is the radius of that circular motions are same?
No, sir, it is not.
No. You have to ask yourself this question. Look, suppose there is a disk. Tell me. Suppose there is a disk. It is in pure rotational motion. Right? Pure rotational motion. This point is fixed. Now you are sitting here. About this point, I want to calculate the angular momentum. Look, this point P. Is the distance from this axis to this point P always fixed?
No, sir.
No. So I cannot use R omega always. Right? So in that case, what equation I will use?
Sir.
Bolo?
Sir, I am saying that rotating in circle with respect to me means separation from me should be constant. So
Yes. From that point or axis, it should be a pure rotational motion.
Okay, sir.
A
Oh, I
pointed
thought
about
it
it get
will
a
look
pure...
it is rotating in circle about the center.
Yes, this body is not in pure rotation about this point,
Okay, sir.
right? So if the body is outside the point, it may have a velocity, it may be rotating with some omega, whatever it may be. Then I will use this formula. Remember that formula, very useful formula. Angular momentum about any point O is equal to IC omega plus MRC cross VC. Similar expression we have seen in energy. Do you remember? Half IC omega square plus half MVC square.
Yes, sir. Yes, sir. I
Yes.
remember.
So whenever you are outside the body, you can say it is IC omega plus MRC vector. RC vector is what? RC vector?
It's that separation from me to
Position
the
vector
center
of C with respect to O.
me. Oh,
O.
yes.
Velocity of C with respect to O.
All are with respect to.
All are with respect to O. But this one is IC omega. What is IC omega?
About C.
It is angular momentum about center of mass.
Yes.
It is also known as spin angular momentum. Spin angular momentum. About
So
center of mass, yes?
So please wait.
Yes.
Spin angular.
It is spin angular momentum, which is angular momentum about center of mass. In order to calculate spin angular momentum, you need to replace yourself in the, you just place yourself at the center of mass of the body and think what is the omega, right? If you place yourself at the center of mass of the body, you will see that there are different omega of the body about center of mass. You find its angular momentum in that way. And what is this part, the second part?
That means I will place myself and calculate the angular
Yes.
momentum with respect to it.
Yes. Place yourself at center of mass.
Yes.
Right. It is the most difficult part because imagination is needed. If you can imagine yourself at center of mass, you can find what is IC omega. And what is this part? What can I say about this one?
The angular momentum of center of mass with respect to you.
Angular momentum of center of mass. Here center of mass can be treated as a particle.
Yes, sir. Yes, sir.
Right. It is a particle only. Angular momentum of center of mass about O. If you can correctly apply this to formula, you will be able to find angular momentum about O.
Sir, please wait for 1 minute, sir. Let me think.
I'm not going to prove this, but I'm sure you can prove it if you try to prove this at your home by applying the same concept I have proved in kinetic energy. The equation I have got in kinetic energy, the same method I have you can apply here also, and you will find this proof. Proof is not at all important, but this application of formula is very important. Find angular momentum of the ring about origin. If it rolls with slipping on x-axis, velocity of center is v and angular velocity v by 2r.
Okay, sir.
Look, angular momentum about O, as O is an outside point, so I can use the second formula, general formula, which is IC omega. IC omega is m r square omega. What is the direction of omega vector? Is it the same here?
K cap. K cap.
K cap. IC omega plus m r cross Vc. Now what is r cross Vc? R cross Vc
is RV.
Is only RV because it depends on the perpendicular direction of the point to the line, right? The velocity line is this one, and from point O to, if you draw a perpendicular, it will be the radius. What is the direction of MRV? MR cross V?
Minus K cap.
Minus K cap. So if you add it, omega is V by 2R, it will be MRV by 2 and minus MRV. So it is minus MRV
by 2 K cap.
by 2 K cap. That is the answer of this question.
Yes, sir. Okay.
Right?
Yes, sir.
Okay. Let us try this one. A rod of mass m length L is pivoted with a ceiling at its top. At the other end, center of a disk of mass m radius r is connected. Now the rod is given angular velocity omega as shown in the figure. Find the angular momentum of the system about the pivot point in the following two cases. The disk is free to rotate and the disk is rigidly attached. Suppose it is the disk and it is the rod. Rod is pivoted at this point. It is rotated with angular velocity omega. What is the angular momentum about point O? Okay. Can you tell me what is the motion of the disk in the first case, translation or rotation?
So it is a rotation.
In the first case, the disk
Translation.
is translational motion. The disk do not rotate about its center of mass in the first case, yes or no?
Sir, so the disc and this rod are both in this plane, so means
Both in same plane.
okay.
In the first case, the disk cannot rotate about its center of mass. Is it clear to all of you?
Mm-hmm.
Because if you look in the first case, if you look, what is the disk? This is the disk. If you imagine yourself at the center of the disk, can you imagine yourself at the center of the disk and how the motion of the rod will behave? If you are sitting at the center of the disk, can you tell me how the rod will move?
So rod will turn, means
The rod will rotate
in opposite, yes, sir.
like this.
Yes, sir.
But as the rod is not rigidly attached with the disk, will the points connected here, all these points, will these points also rotate or it will remain the same here only?
Same, sir, same.
Here only.
Okay.
These points will not rotate. So about this center, will the disk rotate?
No, sir.
No rotation
Sir, no,
about
no.
C. In the first case, no rotation of the disk about C. Yes or no? In the second case, as these points are rigidly connected with the rod, so when
The
you
disk
rotate
will
this
rotate.
rod, these points will also rotate, yes or no?
Yes, sir.
So in the second case, the disk rotates with the same omega, yes or no?
Yes, sir.
About C. Now you can write your momentum, angular momentum. In the first case, and both the cases, rod is about this point. This point is inside point of the rod, yes or no?
Okay, sir. It's inside point.
So I can use, it is fixed point also, fixed axis also. So for rod, no tension. It is only ml square by 3 omega, yes or no?
Sir.
Yes.
So I am confused. So in that first case means that string will get rotated, but that rod disc will remain where it was. So
Yes.
first
Disc will not
case,
remain where it was. Disc will also move. But disc will not rotate, that I have told you. Disc will not rotate about its own axis. The center of the disc is rotating about this axis. Yes or no? But if you draw...
My visualization is totally wrong, sir. Sir, can you please explain this, sir? Elaborate this.
Yes, I have already explained it one time or once or twice if you remember. Suppose I have drawn a straight line here. If it is free to rotate, how the straight line will move? It will remain here only, in this line parallel also.
Yes, sir. So in that first class that you explained like that. So
yes, the same thing, same question actually.
Okay, sir.
This is moving parallelly, so it is translational in the first case. But in the second case, this angle will not change. The second case, this is changing its angle. The second case, it is rotational.
Yes, sir.
Right? Now, about this rod, can I write it is ml square by 3 omega only?
ml square by 3.
About this point, if I say.
Yes, sir, you can.
What about the disk? In the first case, if I say IC omega, is IC omega 0 or not in the first case?
See, it's not rotating only, so it will be 0.
And what is mr cross vc? Center of mass has its velocity, yes or no?
Yes, sir.
Center of mass has its velocity. What is velocity of the center of mass?
Sir, RC at first will not write.
It is L omega. Center of mass is connected at the end of the rod. So what is the velocity at the end of the rod will be the velocity of center of mass? Yes or no?
Sir.
Can't get it? The center of the disc is at the end of the rod. So will it not move with L omega velocity?
Yes, sir, it will move with L omega only. Yes, sir.
Yes. What's the problem with that? And what is the position vector from O to C? It is also
L only.
So is it ml squared
omega? It will be directed to k cap.
Yes, it is also k cap. So this is the angular momentum in the first case.
Yes, 4 ml square by 3 into omega k cap.
And in the second case, can I write the rod to be the same?
Yes,
but
sir.
What is IC omega? Is IC omega now 0?
No, sir, it's now rotating.
It is rotating with the same omega. So is it mr square by 2 omega?
Oh.
Yes or no? Plus mr cross vc term is also there. ml square omega k cap. So it is the second part.
We are calculating at that instant. So
at this instant omega is given only. Yes, after some time omega may change. Also in the second case you can imagine this entire body as a rigid body. Yes or no?
Yes, sir, that only.
And this O point is inside point of the rigid body. So you only need to write the moment of inertia about point O. Is it ml square by 3 plus mr square by 2, then parallel axis is ml square.
Yes, sir. Into omega k cap.
Into omega k cap. That is also another way to solve it. If it is rigidly attached, it's very easy to calculate.